So single displacement reactions, some textbooks I've seen them described as being single replacement reactions. It doesn't really matter what term that our textbook uses. Displacement. One element displaces another element that's in a compound and a new compound is formed. In terms of the general formula, element A, compound BC, it displaces B, B is left alone, and we end up with a compound AC. In this case, A is representing, well, what type of element is A representing out of our two types? If it's going to go into the position where B is and displace B, then what type of element is A in this particular scenario, Janessa? Yeah, it's got to be a metal, because metals come first when we have a chemical formula, right? But we can also have single displacement reactions that involve nonmetals. We can have some halogens displacing other nonmetals in the reaction. So it doesn't have to only be metals, all right? Again, the classic way to recognize it, element and compound. We'll do a single displacement to produce, again, an element and another compound, right? So again, an element and a compound. And again, two of them are becoming two different things, but again, it's element, compound, element, compound. Depending on who taught you grade 9 and 10, where you've learned about single displacement reactions, you might have a teacher that describes some kind of a dance, right? They're dancing together, and then someone comes on, may I cut in? You know, and they look at, okay, you know, the wimpy guy gets out of the way, and the big jock guy takes over dancing, that type of thing. No? Is that the way they describe it all the time? Okay, anyway. All right, but that might have been sexist. We could have, like, the girl coming in, cutting in, maybe. Get out of the way. I don't know how that would work. It would be vicious, though, right? Because girls' sports are much more violent than guys' sports, always. It's a true statement. Don't look at me. You guys know this. My wife, when she was in university, well, when we were in university, did I tell you this story already about how she was on an intramural basketball team? They wanted a coach. They wanted someone to guide them. They said, would you like to be the coach? I said, yeah, no problem. That was the most violent basketball I'd ever seen in my life. And not only is it violent, but when they come off, they remember everything. Number 5, oh yeah, number 5 is good on you, yeah, you know. With guys, it's different. It's not like that. Guys, you know, in hockey, it's like, oh yeah. And then later on, it's like, hey man, hey, how's it going? Hey, did I fight you? I don't know, maybe. Hey, that's cool, eh? And we'll see you later, right? And once it's done, it's done. But girls, they remember that stuff. So a girl cutting in to a dance would be a lot more entertaining than if the guy cut in, trust me. Anyway, I've kind of digressed off the idea of the single displacement reaction, but it's true. All right. So again, just to follow that up, a metal will displace a metal cation from its compound, and a nonmetal will displace a nonmetal anion. So nonmetals will displace nonmetals, and metals will displace metals. We sometimes can have, sometimes things like magnesium can displace carbon. But in an example like that, when we have a molecular substance, one of the atoms is behaving more metallically than the other atoms, right? So sometimes you've got to make a decision on, in the compound, which is the most metallic of the two, if we're talking about a covalent compound. And you don't even really have to think about it, because in something like carbon dioxide, let's say the compound that we're trading out is carbon dioxide. Simply by putting the carbon first, we've implied that this is behaving more metallic than oxygen, right? Oxygen is pulling the electrons towards it closer, right? It's got a higher electronegativity, which means the oxygens are behaving more non-metallic. So we still have the ability, because now we know that there's this degree of change of metallic character and non-metallic character, that we can still deal with that. But under normal circumstances, the metal displaces the metal, the non-metal displaces the non-metal. Okay. So let's look at some examples here. Now at this point, I'm giving you examples where we're just going to trade them out. But in a moment, I'm going to talk about some situations where the reaction doesn't happen. Right? So not only do we have to think about when we trade them out, but we also have to think, does the reaction actually take place? At this point, we're just practicing. Now, the thing I want to practice first is what happens if we have a multivalent metal swapping in? And we've already covered this. You tell me, what oxidation state am I going to use when that multivalent metal swaps into becoming a compound? Which of the two possible oxidation states that are provided am I going to use in order to determine the compound? I think we've mentioned this. We mentioned this yesterday where we talked about forming the oxide. Like if copper was going to burn and you made copper oxide, how do you determine which oxidation state to use? Atlee? You use the most common one, and on your periodic table, where do we find the most common oxidation state? Janessa? It's in bold. So if you've got something like copper, and it's going to swap out the silver, yeah, you're going to end up with Ag, and you're going to end up with a CuNO3. I don't know why I said that. But we need to determine what we're going to cross over. I need to go to my copper, and which one's in bold? 2, so I need to cross over the 2. The most common oxidation state is going to be formed, which means I need to balance this. And that's not too bad. I'm looking at the nitrates. I'm seeing the 2. Now I'm going to put the 2 with the silver, and I think we've got it. Because when copper is in its metallic state, it hasn't gained or lost any electrons. Its number of electrons is exactly equal to its number of protons. It's in its atomic state. And therefore, what's the charge on this thing? What's the charge on this Cu if it's an element in its atomic state, same number of protons as neutrons? Yep? It's neutral. It has a charge of 0. Pure elements have an oxidation state. It's 0. It means they haven't done any trading yet. So what happens here is it goes from being an oxidation state of 0 to being an oxidation state of something other than 0. And you have to look at your periodic table to determine which one to use, and that is 2, all right, in this case. So same thing with iron. Right now, as a reactant, a hunk of iron, it hasn't gained or lost any electrons. Its oxidation state is 0. Then it gets involved in a reaction. It displaces the copper, and now the iron is bonded to the chlorine. I need to go check to see what oxidation state it's going to become, and I don't because you're all going to do that for me, and I'm getting 3 fingers up from many people in the room, so we'll go with a 3. Again, we need to balance. I've got a 2-3 situation here, obviously. You got the whole number there, Abby? 2, 3, 3, and 2. Okay? In the grand scheme of things, I always tend to put the element that's been displaced first. It doesn't matter what order those products are in, right? If you were to put the compound first and the element last, it's immaterial, right? The order doesn't have any meaning there. Right? And in this case, we've got chlorine. Chlorine is a nonmetal. It's going to displace the other nonmetal. So I'm going to be left now with Br that's been displaced. It's a Hofbrinkel, so I do need the 2. And I'm going to have the Na with the Cl. And Na only has one oxidation state, right? There's no thinking involved there. That's 1 and 1. And now I just need to balance, and it's looking like I need 2 and 2. Okay? So last year, I don't know how much depth your teacher went into. It depends on you know, whether your teacher is a chemistry trained or not. They may not have had you worry about questions that had multiple oxidation states. So that might be a new addition to this, right? Swap them out, and then for those that have multivalent ions, you have to pick which oxidation state to use. We okay with that concept? Okay. Now, like I said, not every single displacement reaction occurs. And actually, I'm going to do a demonstration with the copper and the silver. I got to get my goggles out of here for a minute. Goggles are in the station. Now here's the second add-on to your single displacement knowledge. Now again, you might have had a teacher that demonstrated this last year, and if you did, that's great. And what I'm doing here is I'm taking some copper wire, and I am actually going to do the reaction that we looked at on the previous slide. It's this one here. Take some copper metal, and I'm going to react that with some silver nitrate. And silver nitrate is a dissolved form of silver. It is silver in the +2 state, all right? So, sorry, +1. It is silver in its classic +1 state, reacted with a nitrate, and then those ions are going to be reacted with this copper metal. So let's just wind this up a little bit, make kind of a spiral. And I want to kind of hang it in the beaker here off to the side so we can kind of see what's going on. So I'll put a little hook on the side. And I'm going to turn on that camera for a moment so that you can all see a little better what's going on. So let's go with input. No other input signal. That's because I didn't plug it in. Oh. Let's try to do this without bumping it. Success. Okay. Let's try that again. Input. Oh, success. And that's not a very good picture. And it might be a little disorienting because we're looking down into the beaker there. All right, that's pretty cool. And let's take some of the silver nitrate. Oh my goodness, it's tight there. And let's pour that silver nitrate in there. What's that? It is actually. I changed my mind on this because silver nitrate is expensive, and I do want to conserve it. Let me get a smaller beaker. I need to make it smaller. Let's do it this way. It's probably enough silver nitrate to do this twice. Yes, silver nitrate is expensive because silver is expensive. And even though the silver is dissolved, it still has to be taken from silver metal. It has to be created from silver metal. So there is a cost associated with it. Here we go. Now we got a smaller beaker. And I'll use that this afternoon. Okay, let me get this out of the way. Now, you can all see the copper metal right there on the edge. You can see it's nice and shiny. Looks like copper, obviously. And I put it in with the silver nitrate, and I don't know if you can see it yet, but I can see it down here on the edge. You guys can probably see it on the side. You might be able to see it from the top, but you'll notice all of this stuff in here is starting to turn gray. And what's happening is the single displacement reaction is happening. We're having silver ions making contact with copper atoms. They're doing a swap in position. The copper is going into the solution, and the silver is actually sticking to the wire. And that's why the wire is looking like it's getting fatter and fatter, because little thin crystals of silver are starting to grow out from this particular reaction. All right? So we'll look at this a little bit later on. Another interesting thing to note as time goes on is that as the copper goes into solution, it turns out that copper ions have a very distinct color. When you burnt the copper in the flame, do you remember what the color was? It was a green. It's technically a blue-green. It's like a turquoisey type thing, and that's because copper 3 is green, but copper 1 is green, but copper 2 is blue. That's always true for copper. Copper in a number 2 oxidation state always has a blue color. You can remember that by saying copper 2 is blue. It's fun to say, and it's true. It's kind of neat. Copper 2 is blue. Anyway, as the copper 2 gets formed, our solution should start to turn blue because we're getting copper 2 in the water now, all right? So we'll leave that sitting there. We might not see the blue by the end of class, but if I leave this over the weekend and let the reaction continually go all weekend, we should see a blue solution in there come Monday. So let's just, we'll just shut that off. We'll let that do its thing. You can watch it directly. We'll put it on the screen as we go on. But if I were to take a hunk of silver metal and put it back into a solution of copper 2, all right, copper 2 nitrate, it turns out that that reverse reaction doesn't happen. That reaction isn't going to take place. So I can't just take any metal and stick it with any solution. Some of them are going to react, and some of them aren't going to react. And that's what I need you to be able to predict by the end of this lesson, which react and which don't react. All right, so that's the next part of this. And it has everything to do with something called the activity series. And this is another chart that you will have on your information sheet. So when you're done writing this down, you can get that sheet out and track down the activity series. Now, my activity series might look a little different than yours. I can't remember. What did I put on the back for yours? Nope, no, it does look like that. It's the same one. You don't have to write the chart. You've got the chart on your periodic table, so you can get your periodic table out and we'll take a look at where the chart is. We already know that some elements are more chemically reactive than other elements. Just as a review, where do I find the most reactive metal? What is the most reactive metal? Francium, right? Down in on the left and way down in the bottom. I could make you think about why that is, but you would all make funny faces as you attempt to think back to that first unit. You'd all go, there was something there. Anyway, it had to do with, what does it have to do with? Does anybody remember? I'm going to make you think about it. What's that? Has to do with ionization energy, right? It's got a low ionization energy. So we know that. And we can rank them within a period, within a group easily, right? Francium is the most reactive. We can also rank them in a period, right? You go to the left and it's the most reactive metal, right? But what chemists have done here is they've not just ranked them up and down and left and right, but they've gone through all of them and they've built a ranking of the important ones. So we don't need to think about where it is on the periodic table. We can use the activity series to basically talk about the most reactive ones and then down to the least reactive ones. And if you take a look at that series, lithium, potassium, barium, strontium, calcium, sodium, magnesium, aluminum, you'll notice we start up over here and we work our way across down into this area where we have then the least reactive metals that are getting up against the stair-step line. And it doesn't work as nicely as we said all the way going up. It kind of scatters itself around, but it works our way across here. So essentially, at the very bottom, we have the least reactive metals, all right? And you'll notice at the very bottom, we have gold, one of the least reactive metals that exist. Platinum might be close to it, but I think gold is even more unreactive. That's why when when people who dig for gold, prospectors, miners, that's what I'm looking for. When miners go digging for gold, when they find the gold, they find it as a hunk of gold. They don't find it as gold reacted with something, right? It's not like they find a rock that has like gold nitrate in it, and then they've got to react it to get the gold out of it. In the ground, if you're going to find gold, you're going to find it as a hunk of gold. Now, if you go looking for something like potassium, you will not dig a hole in the ground and find a hunk of potassium. It just doesn't happen. Think back to what happened to the potassium when we put the potassium in the water. Do you remember what it did? It caught on fire. If there's a hunk of potassium hanging around for some reason on the ground outside, what happens to it? It goes, well, it actually would oxidize just in the air, but if it started to rain, that'd be exciting stuff, right? So walking down the street, minding your own business, looking on the ground there, whoa, look at there. You might find a ring or a piece of gold, that jewelry that somebody has dropped. It might have been there for days, for years, doesn't react in the rain. But you will never walk down the street and go, oh, look at a hunk of potassium sitting right there. Oh, I could have some fun with that. I better take that with me. And that's because gold is non-reactive and potassium is highly reactive. All right? So gold is non-reactive and potassium is highly reactive. We had a pen explode. All right? And keep that in mind when determining how to determine whether the reaction is going to take place or not. Any elements that are at the bottom, if they have the opportunity in a single displacement reaction to get themselves by themselves as atoms in an unreactive state, they will. Because elements at the bottom of the activity series, for some reason, due to their low reactivities, want to be alone in nature. They're the loners of the metal world, all right? They do not want to be in a reacted, bonded state. So the elements at the bottom want to be alone if given the opportunity in a single displacement reaction. And the elements at the top are highly reactive. If they're alone and they have an opportunity to swap out and become a reacted thing bonded to a another ion, then they will. So the key thing to be able to remember this is the ones at the bottom, they want to be alone. They'd rather be in a non-bonded state. Now, in my next slide, and don't write this down. In my next slide, I have a rule, but it's full of great techno jargon. A metal atom will displace a metal cation that's below it on the activity series. That's a true statement. But to distill that down, the ones at the bottom want to be alone. That's essentially what it is. So let's write that down, because that's probably more useful than thinking in terms of atoms and all that stuff. So let me just get the pen ready here. Let's write elements at the bottom of the series want to be alone, all right? And when I say alone, I mean they want to be in the elemental state, all right? They want to be in their elemental states as atoms, not as ions, okay? Now, I've got some other text that comes up here. I always say that I want to change this PowerPoint. But let's just do an example here. And you'll notice I've got the example in the space there. Iron and copper sulfate. So I'll just clear that up. I'll just write it here. Example, Fe plus Cu SO4, and it's copper 2 sulfate. And the question is it going to happen? Are we going to get a chemical reaction? So here's how you do this. Iron, it's going to displace copper. Go to your activity series. Find the two of them. Take a look at which one's on the bottom. Which one's on the bottom between iron and copper? Yeah, Janessa? Copper. Which one wants to be alone? Is it? Will this reaction happen? Yes. It's that simple. All right? The ones at the bottom want to be alone. Iron and copper. Copper is below iron. Where is it down here? Right there. It wants to be alone. It isn't. We swap them out. Therefore, we're going to end up with copper metal plus some kind of iron sulfate. And because iron is multivalent, I got to determine which it is. Which one is it? 3. Sulfate is 2, right? So I think I need a 2-3 scenario here, I think, right? Which means I need to do some balancing. Looks like I need 2 of these guys for the iron. And I'm going to need 3 of these guys for the sulfate. And therefore, I'm going to need 3 of those guys for the copper. Right? Did I do that right? Okay? The elements at the bottom want to be alone. Okay? Let's do another example here. And we don't really want the explanation. That's great. That's good. We've got the explanation down. That's beautiful. Ag plus MgCl2. Locate silver, locate magnesium. Which one's on the bottom? Silver is it which one wants to be alone? Silver, is it alone? Yes, nothing's going to happen to this. No reaction. No RXN, no reaction. All right? You want to be even more lazy? No reaction. I don't care which one you use. You could actually write out no reaction if you'd like. That'd be crazy, though. So many letters wasted on such a thing. All right. And that's great. We know the explanation. Let's do a non-metal example. And don't even write down that a non-metal atom will displace a non-metal anion that's below it on the periodic table. Okay. Same thing is true. But now you'll notice you don't have the halogens on your activity series. But don't worry about it, because the periodic table supplies us with an activity series. Right there. We're going to be talking about the halogens displacing other halogens, and right here is the activity series. We already know which is the most reactive of these elements. Yeah, Emily? Yeah, fluorine's really reactive. It's not going to be content to be alone. It's going to be in the reactive state. Down here are the least reactive ones. They're going to want to be alone. The same is true, except group 17 becomes our activity series. So here we're looking at chlorine and iodine. Those are the two we're comparing. I find them. Which one's on the bottom? Which one wants to be alone? Iodine. Is it? No. The reaction will happen. Swap them out. All right? So you will use this as your activity series for the nonmetals. And iodine wants to be alone, so yeah, it's going to swap out. We're going to get I2, and we're going to get NaCl, and then we've got a balance. Which means I think I need a 2 and a 2, and I think that does it. Okay? So for nonmetals, we use the actual halogen series as our activity series. No need to have a separate one. And again, no need to write this down. Chlorine will displace iodine from its compound because chlorine is above it. And that logic uses an above logic, and I like to use is it at the bottom logic. That's the one that I like to think of. And the reason I like that logic is because if if I ever forget it, let's say you're on a test and you are starting to panic and you forget how you determine which is which, but you know you have to use the activity series. This is the reason why I like the one at the bottom wants to be alone. What's at the bottom of your activity series? What's that? Gold. How do you find gold in nature? As an ion or as a hunk of metal? As a hunk of metal. Gold always wants to be alone. It wants to be just as gold. And that's what triggers my, oh yeah, gold's at the bottom. Gold is non-reactive. It wants to be alone. The guys at the bottom want to be alone. Right. Then I can get through it. Even if I've forgotten that, I can use that gold as the anchor to help me answer the question. Okay. Iodine, fluorine. Iodine's at the bottom. It wants to be alone. Is it? No reaction. No reaction. Right? Okay. Let's do some examples here. So just put EG. And you don't have to write complete and balanced. Obviously, that's what we're doing here. And I'm just going to put a bunch of them up here and let you kind of work through them. These you can do. There is a specific one, though, that I want to get to. And actually, I'm going to go grab some apparatus for another little demonstration here. Hello, Jimmy. Okay, so why don't you guys tell me what's happening here? I'll take the products and their formulas, and then you can tell me all the coefficients. And if one of the coefficients is just a 1, just say 1. So what do I have as the products here? Or if it's no reaction, just tell me no reaction. Yep. No reaction. Chlorine's at the bottom. Excellent. Let's get the pen going here. No reaction. Beautiful. Next. Somebody have some products for this? Janessa, what do you got? Just give me the products for now. So Ni, and how many Cl's on this? 3 plus Pb plus lead. And then just give me the coefficients. Tell me what numbers I have to put in front of these things. 2, 3, 2, and 3. So you're telling me lead is below nickel. Excellent. Very good. And the last one. Oh, and did you have chromium on your list? Yeah? All right. So tell me what we have for the last one. Tell me products first, and then we'll take the coefficients. Yep, go ahead. Oh, no reaction? Oh, that's fun. No reaction. So potassium is, potassium's right at the top of the darn thing. Crying out loud. It's very reactive. Should have saw that one coming. Let's do a couple more here. Nope. That's right there. I can do those. By the way, this is ALI. A little confusing. It's ALI. And you know what? Stop at 6 and 7. I will work through these two with you. This one, again, magnesium is reacting with a molecular substance, but by putting the H first, we're implying that it's the most metallic, all right? So it is the most metallic of those two elements. And you'll also notice on your activity series, hydrogen is on there. And that's because hydrogen has this ability to sometimes behave a little bit like a metal. So you can do 4 and 5, and then I'll stop at 6 and explain why I put an HOH instead of H2O. So maybe you're already done 5 and 6, because they're pretty straightforward, I think. Again, I will take products and then give me the coefficients. Somebody have it for 4 and 5. Somebody have it for 4? Products and then the coefficients. Janessa, what do you got? Sorry, I2, did you say? What would you say? It would be I2 because it's a Hofbrinkel. Did you want to say I3? Is that what you put? Oh, okay. Oh, all right. It's an I2. It's a Hofbrinkel. I2. And then aluminum bromide. What's the formula going to be? AlBr3. Excellent. And then to balance it, what do we need to do? 3 here. 3. 2. 3. 2. Yep, that's one of those 6 things. All right. Excellent. Good. How about this next one? What do we have there? What are the products going to be? Yep, Brendan? What's formula going to be? Yep. H2, very good. H2. And let's balance that up. What do I need? Yeah. No, that's good. Excellent. This reaction of a metal with an acid will pretty well always produce hydrogen gas. That's how I'm going to generate my hydrogen gas in order to make my hydrogen balloon when we do the demonstrations. It's going to be essentially a metal with an acid, and that produces hydrogen gas. Excellent. Let's take a look at this one here. Now, I'm reacting the potassium with water, and this reaction will take place really with any metal that's above it, above hydrogen on the activity series. We call these active metals because they're ranked up against the hydrogen. Now, if I were to put this as H2O, we would get the wrong answer. Because you'd look for the hydrogen, you'd look for the potassium, you'd say the hydrogen was on the bottom. That means hydrogen wants to be alone, and you'd trade them. But we have to be careful with this one, and let me show you with a demonstration. I'll just show it to you right here. I won't even put it on the screen here. Here I've just got some water, and I've already done this demonstration for you. I'm going to take a piece of potassium, and I'm going to put it in the water. So let's get my knife and my super tweezers here. And I'm going to get a little piece of potassium. There should be one nicely at the bottom. Yep. Now that's a monster piece. That would be dangerous. So we want to avoid danger. So I'll cut a piece off. And you've already seen this. This is just for me. This is just so I can burn something in a day, right? Because I haven't burnt anything yet. So really, this is for my benefit more than yours. Because I can. That's why I like doing these things. But I'm going to add some phenolphthalein to it. And I think I did that last time I showed it to you as well. What's the purpose of phenolphthalein? what is phenolphthalein called? It's not a base. It's not an acid. It's an indicator. What does it indicate? It indicates acids and bases. Now, I don't know if anybody remembers the colors for phenolphthalein. You would have saw it when I did the demonstration last time. Do you remember? Pink and colorless is the other color. Does anybody remember what the pink color goes with, an acid or a base? Janessa? Oh, 50-50. Try again. Don't go buy a lottery ticket today. Base, right? So it's pink when it's a base. Now that's very important because, did I already add the drops? I think I did. Because let's take a look at what we get when we react it, all right? We get fire, which is just fun, right? It's spitting, it's exciting as well. Let's stir it up. What did it produce in the end? It produced a base, which means what ion must be in there if it produced a base? It has to be a hydroxide ion in there, right? If you did this reaction like this, K plus H2O, what would you predict the products to be? It would be incorrect. But what do you think the products would be if you just traded them? Somebody tell me what they would be. Yeah, Atlee? Potassium oxide and hydrogen gas. Excellent. Now that's K2O because we'd have to cross it over. Is there a base in the products there? No, which means that is not the correct reaction. If you think of water as being a hydrogen bonded to a hydroxide, so you have hydrogen bonded to a hydroxide, now when the displacement takes place, what are you going to get for products? Potassium hydroxide, KOH plus. And what's going to be left? H2, because two of them will get together when they react, H2. And that's what the bubbles were, right? You know that bubbling and dancing around? That was hydrogen gas. It actually ignited from the heat of the reaction. That's what that flame was around the potassium hydroxide. That was the hydrogen gas burning. And the nice little pink flame was some of the potassium atoms that were so hot they were flying off of the metal and getting caught in the flame and giving us a nice little flame test color for potassium. Now, I'm going to give you a warning. On the test, I don't tell you that it's hydrogen hydroxide. I just write down H2O. And I need you to think that it's hydrogen hydroxide in order to get the answer correct. It is mean. It's a little mean. But if you think about what I did here as the demonstration, you know you need hydroxide as your answer. So you can maybe logic it out. All right? So that's an important one. And that's going to be true for any reactive metal. I can get the same results for any of these. Now notice if I put a hunk of lead in there, it's not going to be nearly as exciting as this. And that's because the rate of its reaction would be super slow. I'd have to leave the lead in that water for like a year, and it might turn the water a little pink and produce such a tiny amount of hydrogen gas that you wouldn't even notice it. But it would happen. It would happen very slowly, all right? It just means that lead is not nearly as reactive as potassium, but it would still happen. But notice my next one. If I put gold in water, right, walking down the street, rainy day, feeling blue, I don't know, so I feel a country music song coming on here. Anyway, and you come along something that glints on the ground there, and it's a gold whatever. If it's a country music song, it's the gold ring that your ex-wife threw out when she left you, and you're going to pick it up and find your lost dog and fix your pickup truck. And anyway, what's the reaction here? No reaction. No reaction. No reaction. All right? Okay. So that tricky one, and that's going to be true for any of those active metals. And now you got some practice problems and plenty of time. I roared through this lesson today, but I do not want to continue on talking about double displacement, so you can get all that work done. Since we're on the country music, you can get her done. And then that's it. Now I'm out of stuff. I'm out of country references, redneck references. Get her done, and I don't know. That's it. That's all I got. All right.